My name is Rebecca Bilbro. I am here from Washington, D.C., which is where I live and where I work. I work at a company called ICX Media. I'm the head of data science there. And I'm also the co-creator of a Python, open source Python library called Yellowbrick, and that's going to be a big part of today's talk. Yellowbrick is a tool for doing visual diagnostics for machine learning. So when I say machine learning, let's make sure we all have sort of a shared vocabulary about at least what that means. So when I say machine learning, what I'm thinking is that we have some set of data samples, right? So maybe you would picture these as rows in a table, let's say, and each of those rows is represented by more than one number. And so those numbers tell you something about that row in the table. And what we want to do with machine learning is to create a model that is able to make predictions about properties of rows that haven't been added to the table yet. And so maybe we'll know some things about those new rows, but we won't know other things. So can we build a model that will be able to infer those things that we don't know about the new rows? In practice, when we do, so that was sort of the formal definition of machine learning. In practice, when we do machine learning, it's often more like this, right? Where, you're in a classroom, if you're a student, or you're talking to a colleague, or, worst case, you're on Stack Overflow, or somewhere in the depths of GitHub, and somebody is just trying to drop knowledge on you and tell you that some model is the best model always, and you should always use that model. And so sometimes it's random forest, but sometimes people are very committed to, support vector machine models. Other people are really gung-ho about deep learning models, particularly right now. And so I would like to suggest a different approach, right? So not sort of picking models based on strong emotion, but on science. And so here is kind of my proposal for how to think about model selection. I would like you to think of it not as just picking the right algorithm, but I'd like you to think of it as a series of triples. And this idea of the model selection triple comes from Arun Kumar in a paper that's actually about next generation databases. But I think this idea of it's these phases where we start with feature selection and then maybe feature engineering as part of our feature selection process. Then we select models and we try many different models, and then we do hyperparameter tuning. And so this talk is going to be a walkthrough of those three phases. But you should also kind of keep in mind that in kind of real-world machine learning, it's very iterative. So for a single machine learning problem, you may iterate through this triple multiple times. If you don't get it right the first time, it doesn't mean you're doing a bad job. It means you have high standards and you want to go through the triple again to get a better performing model, and that's okay. Okay, so what is Yellowbrick? Yellowbrick, as I said, is an open source Python package. It's hosted on GitHub. The documentation is on Read the Docs. So you have access to all of the code. It's all open source. And it is built on the scikit-learn API. Has anybody experimented with the machine learning library scikit-learn before? It's a Python library. It's a little bit like Caret for the R users, right? So it's a single library that provides access to many different machine learning algorithms. And scikit-learn is incredibly popular because it has a consistent API, which means that you can wrangle your data one time and then use any of the models without having to reformulate your data each time. And this did not exist essentially before scikit-learn existed. So what Yellowbrick does is it hooks into that API and adds a visualization layer using matplotlib plotting routines so that you can get insight into how your model is performing at each of those phases that I showed you in the last slide. So I'm going to walk through those three phases using Yellowbrick, and that'll be the talk. How's that sound? Good? Okay. Okay, step one, feature analysis. What is feature analysis? Basically, it's finding the smallest set. You're trying to down select all of the columns if we're still kind of thinking about our data as a table, and the instances are the rows. The columns are the features. The columns are the things that tell. And so what we want to do is down select those features as much as possible to get to the smallest subset of features that is maximally predictive. And the reason we need to get to the smallest subset is because as we have redundant features, we inject noise into the model, and so our performance is going to go down. It also, frankly, with really high dimensional data, excess features just make model fit take a really long time. And so there's sort of practical constraints too. So we want to try to shrink the feature set. So how do we do that in a sort of thoughtful, scientific way? So what I would propose is you first think about separability, and this is mainly for doing classification problems. So for supervised learning classification problems, we want to start by seeing, is the data separable, or are the data separable, if you're a grammar person? There's always a few in the audience. So, one way to hunt for separability is to look at something like this. That now is a radial visualization, or RADVIS. So we've got our features distributed on a unit circle, and the way that it works is we drop our points from our table into the center of the circle, and we let the feature points according to their normalized value. So if temperature is really high in unoccupied rooms, so that's what we're looking at here. Each row is a data point about a single room, and each feature describes the room. It tells you how hot the room is, how humid the room is, how bright the room is. And so what we're doing is we're putting those features, brightness, temperature, humidity, on the outside of the circle, and we pull the points according to how hot the room is or how bright the room is. And what we're hoping for is that we see a difference between the rooms that are empty and the rooms that are occupied. And so we've colored those two different kinds of rooms different colors to see if we have separability. And do we have separability? It looks like we probably do. If we're not sure, we can double check using another visualization that's similar, that's called parallel coordinates. And so what we have now is we took that unit circle and we spread out the features to be the x-axis. And so now the features are these vertical lines, and the points, instead of being single points for each room, it's a connected line segment. And what we're looking for now are bands of similarly colored line segments. And what that tells us is there is separability, and that gives us a good sense that this is a good for machine learning. This is gonna give us a good opportunity for separability. So the next thing we want to look for, so we look for separability. Now we want to make sure we understand if there are any correlations in our features. And so the kind of main correlation you want is you want some correlation between the features and the target, because that's how you make predictions. So there needs to be some sort of relationship between the columns and the label, the true value for your supervised learning problem. And you can visualize this by fitting kind of an initial model and looking at how correlated each of the features is with the target. And this is very helpful for starting to identify weaker features that are maybe less informative to the model. You can also use this to see if some features are more informative to certain models and less informative to other models. Another kind of correlation we need to be looking at are correlations between features. So this is a different data set. This is not the room data set. Here we're looking at credit payments. So we're looking at people paying down their credit balance each month. And so, month over month, we're looking at how much they owe and how much they pay down. And you probably have some intuition. There's probably some relationship month to month, right? If you have some debt one month, probably some debt the next month, it's not going to result in kind of completely unrelated features. And we see that very strongly in this plot, where we have very dark, like maroon colored squares and very dark blue squares, which show strong correlations between the features. And this is a very helpful plot. It's called rank 2D. And it helps us see that we have some strong interrelationships between the features, which is going to cause noise in our model. With this, when I see a plot like this, it tells me I need to do feature elimination, because I've got features that are redundant and are going to interfere with good modeling. Okay, the next thing we want to do is look at the distribution of the data. This is going to be particularly hard if we have very high dimensional data. And so one of the tricks for high dimensional data is doing dimensionality reduction. So one way to do dimensionality reduction is using principal component analysis. So we compress all of the dimensions, all of the columns, let's say in our table, into, let's say, 2 dimensions, and we do a scatter plot. You can do a PCA projection plot in 2 dimensions or 3 dimensions. Beyond that, it sort of starts to be not interpretable to human brains. But you can do 2 or 3 dimensions, and what you start to see is you're able to see the distribution of the data along the 2 principal components, and you can see if there are outliers. And if there are outliers, that starts to give you an intuition that there might be some modeling challenges here. Maybe we need to do a little bit of cleaning before we can kind of depend on good modeling. Sometimes relationships are not linear, and in that case, a manifold is a good alternative to a PCA projection. It's another way to compress very high dimensional data into fewer dimensions and do a scatter plot. But it helps us see that there are latent structures in our data that can inform how successful our modeling is going to be. And then I want to just point out that this also works for data when you might not expect it. I work with a lot of text data at my job at ICX, and so I often have to deal with extremely high dimensional data, right? So if you think about text data, every word is a dimension. So if you have a document that has 100,000 words in it, you have 100,000 columns, let's say. It's extremely high dimensional. It's very hard to wrangle, but you can kind of compress it very easily using yellow brick tools like this. So what we're seeing here, the scatter plot here, is a stochastic neighbor embedding plot, and what we're looking at is the distribution of a bunch of documents from a corpus colored by their category. And so you can kind of see if certain categories are grouping together, or if some are very diffuse. If they're diffuse, they'll be hard to model. If they're grouped well, they'll be easier to model. You can also do token frequency distributions to see which features are most informative in your text corpus, so you can get rid of ones that are less informative and compress the dimensionality. You can also do interesting things like part-of-speech tagging plots. So I'm not sure if anybody here does natural language processing, but part-of-speech tagging is a big part of successful machine learning on text, because you need to know what function words are playing in a sentence. And so here we can look at a very high level, kind of what functions words are playing in a corpus. So the next phase, right, remember, so we're moving through these circles, right? So we're on the second circle now, model selection. But I would like to argue that instead of model selection, what we really want to do is model evaluation, because we have access to scikit-learn. So why would we just pick one, why would we select one model when we could just experiment with all of them? But before we go down that path, we need to make sure we know what matters to us, because not all evaluation techniques are sort of created equal. Let's say we're trying to evaluate a classifier, right? We started with that problem where we were trying to decide, can we separate empty rooms from occupied rooms in our data set? But what really matters to us for our problem? Do we want to try to minimize false positives where we think something is empty, but it's actually occupied? Do we want to try to minimize false negatives? Do we need to compare a lot of different models together? Are our classes imbalanced? Do we have a whole lot of empty rooms and only a few occupied rooms? Those things will determine which kinds of metrics we want to use to evaluate our different classifiers. And so we don't want to just sort of like pick accuracy because it's the easy one to use to evaluate our models. We want to pick a evaluation metric that's relevant to our specific use case, right? And so trying to decide between rooms that are occupied and unoccupied is a very different problem from trying to build an app that tells you which mushrooms are edible and which ones are not, right? So you need to think about how to evaluate your classifiers based on the specific problem that you're trying to solve. ROC-OC is a way to think through the trade-off between false positives and true positives, right? This is, ROC-OC is not a new kind of visualizer. You can do it in Yellowbrick, and I think it is helpful for starting to get an intuition about that trade-off. Basically, what we're looking at here is that the trade-off between, as we get fewer things wrong, right? So as our true positives increase, so do our false positives, right? So getting more right comes at the expense eventually of getting more wrong. And so what we're hoping is that we'll see something like this dotted red line, so it's pulling up to the corner here. What we don't want to see is something like the vertical, the 45-degree black line, right? That means that our model is a coin flip, and it's not a very good coin flipper. I think that this is different, very different from a ROC-OC curve, but it's using very similar information. You might recognize the term confusion matrix. So confusion matrix is another kind of visualizer. And we do have a confusion matrix visualizer in Yellowbrick, but this is our twist on it, which I think is a little bit more interpretable or less confusing. And so what we're looking at here is on a per class basis. Here we have 5 classes. We're trying to differentiate between different kinds of fruit based on their features, their color, their size, their shape, let's say. And so what we can look at is on a per class basis, what kinds of mistakes are we making? Like when we get our classifications wrong for oranges, what do we sometimes think they are? What are we most likely to misclassify them as? And it looks like when we get our guess for orange wrong, we mostly think it's an apple. So maybe we need more information about color to help differentiate our model, right? So this is a really good way to start to get an understanding not just of when things are going wrong, but why they're going wrong. Evaluating regressors is similar, I'll argue, to evaluating classifiers in the sense that it's also a supervised learning problem, so we know the true value. And so out of curiosity, so we're looking at 3 different models here. I don't know how easy it is to see. We're looking at 3 different models. The dark blue points are the training data. And then we see a green line and a few different versions of the blue line. So in the first one here, the blue line is a single line, right? So that's the most simple model. It's trying to fit kind of the general trend of the data overall. The next one is kind of this kind of simple curve, right? That's going through, maybe not all of the points, but it's kind of has that general trend of the data. And then the last one goes through the blue line goes through almost every single point. So it captures almost all of the signal from the original data set. Which model is the best one? The middle one, but it doesn't go through all the points. Right, so sometimes points are wrong. And what that means is, we want to fit our model to the general trend of the data, but we don't want it to overfit. Because if it's overfit, it will not generalize to new data. As we add new rows to our table, they're not going to fit that very specific shape of this kind of crazy model that's going through all of the points. And the way that we achieve that middle model is through regularization. We'll talk about that in a few slides forward. So one way to kind of get a sense of how well your regressor is doing is by using a prediction error plot. And this allows us to kind of see the error as a 2-dimensional scatter plot where we're comparing the predicted values to the actual values, right? And so we would really like them to line up perfectly with the 45-degree line, right? Because that means we made perfect predictions every time. But that's probably not going to happen. And so what we have here is we have that 45-degree line plotted in light gray. But then in dark black, we see the actual line of best fit between our predicted and actual values. And that gives us the sense of how far away from ideal is this model. We can do something similar with a residuals plot. And so in Yellowbrick, you can essentially take that 45-degree line that we saw in the last plot and turn it to the 0 line. And so what we're looking at now is, and we've colored the training points and the test points different colors just so we can compare those. But what we're looking at now is how random are the residuals. We want them to be random. If they're not random, it means our model didn't capture something in the original data set. And so when I look at this, what I see is heteroskedasticity, which means I see this sort of funnel shape that here the points are very close to the 0 line, but as we increase the value, they start to spread out. And that means that there is a distribution issue that is going to complicate modeling. And so we're going to have a lower R² value here than maybe we expect, because some of the points are much differently distributed than other points. We should also try all the models, right? Don't just pick random forest because somebody told you that random forest is always the best way to do it. It's very easy with yellow brick to just try them all and compare them, right? So this is a prediction error plot, 3 different kinds of algorithms, same data set. You can pretty quickly tell that one of the algorithms is not a good candidate for this data set. Which one should we not be doing? The middle one, right? And so it's probably too hard to even read, from there what different kinds of models these are, but you can sort of tell that it doesn't really matter, right? Your kind of visual intuition quickly looked and said, there's something wrong in the middle. That one did not capture the best fit line. It's nowhere near the best fit line. All right, last tip for model selection / evaluation is always think horses, not zebras. So this is something that I explain to my students every year. I teach as an adjunct at Georgetown University in DC, and generally people come up with these very complicated ideas of why their model is not performing, like there's a conspiracy against them. But generally that is not the case. Generally it's one of a few things. It's probably a class imbalance problem. If you're doing classification and your classifier stinks, it's probably because one of your classes is severely underrepresented in the data set, and so your model is just not ever classifying anything as that class, because it almost never happens, and so your model is almost always going to be right if it never picks that class. So what do you do if you have a class imbalance problem? Well, you should probably go and get more data, but sometimes that's not an option. And so if that's not an option, you can experiment with different things like oversampling. You can oversample the underrepresented class, or you can try stratified sampling to see if there are certain chunks where you can get the model to perform a little bit better. Another great trick when you're kind of in zebra mode is to use this cross-validation score visualizer. And so your intuition, we've looked at this already, where the data is not always evenly distributed, right? We've already seen heteroskedasticity. We've seen some problems like that already. We should have an intuition that our model might perform better on certain parts of the data than on other parts of the data. And we can actually see a very clear example of that here. Here we've done 10-fold cross-validation, and for all but 1 fold, our model is doing amazing. But for the first fold here, its score is significantly lower. There's something going on in that subsection of the data, right? We don't know what it is. Are there some outliers? Is there some noise? We don't know. But if this were me and I had this data set, I would dig into that fold and figure out what was going on in that section of the data, because there's something there that I wasn't expecting. Okay. Last bubble, right? So we're going through the 3 phases here of the model selection triple. We've landed on the last one, hyperparameter tuning, but you guys already all know what hyperparameter tuning is, so we can just skip these slides, right? Okay, hyperparameter tuning is like the hard part of machine learning, right? So there's all these tutorials like learn machine learning in 36 hours and then you're a data scientist and, bam, bam, boom. But like, honestly, learning how to use scikit-learn and learning how to kind of nimbly tune hyperparameters to get really high performing models is sort of the difference between that 36 hours and like, more hours. So my advice to you is to just start with using the defaults, right? Scikit-learn comes with very reasonably selected defaults for hyperparameters, and you should dig in and see what the defaults are. But you shouldn't feel like you have to modify them too much in the beginning. What is a hyperparameter after all, right? So parameters you've probably heard of, right? Function parameters are things that change as the function learns the data. Hyperparameters don't change. Hyperparameters are things that you provide the model. And so examples of this are like, how deep should I make my decision tree, or how many leaves should it have? How wide should it be? How deep should it be? What kernel am I going to use for my support vector machine? Am I going to use a radial one? Am I going to use a linear kernel? How many clusters should I pick for k-means clustering? Those are all hyperparameters. And so what I'm going to suggest is you just start with the defaults, but maybe go and look in the documentation, find out what the defaults are, because those are informed by people who have been doing machine learning for many, many years and have a good gut sense of what a good starting point is for those hyperparameters. What people will tell you to do is to do grid search, right? So who's heard of the term grid search before? Okay, so if you haven't, write it down and look it up later. But TLDR is that grid search is like a blind journey, and you're searching a massive decision space for optimal hyperparameters. If you don't already have kind of a gut sense of what values you should be searching between, you could be searching for a very long time. And even if you succeed in finding optimal hyperparameters using grid search, you may be at a local maxima and not the global maxima, which means that you might have found a few hyperparameters that get good when you search in this space, but if you had only searched over here, you would have gotten to a much higher performing model. And this is what automated machine learning tools try to do, this grid search on your behalf, and they miss global maxima all the time for this exact reason. So my suggestion, like once you're ready to kind of move past using the defaults, you start to get a sense about what hyperparameters even are, is to use Yellowbrick to do a visual grid search. And so I'm going to give two examples of how to do this. One is with centroidal clustering. So this is when we're doing unsupervised machine learning and we're looking for clusters in our data. So in k-means clustering, you have to tell the model how many clusters to fit the data into. But how do you know how many clusters to pick? It's just a guess. People have heuristics for it, but ultimately it's just a guess. And so what we're looking at here on the left-hand side of the screen is a silhouette plot. And so this is plotting each of our clusters. Here we've specified 6 clusters for this model. It's fit our data set into 6 different clusters. And this red dotted line is the average silhouette score. And a silhouette score is essentially telling you how dense the cluster is and how separate the clusters are from each other, because that's kind of a measure of how good they are. And so what we see is 4 of these clusters are pretty good. They're pretty dense. They're pretty separate. 2 of them, not so good. They're kind of diffuse. They're maybe a little bit overlapping even. And so we can tell that they're not doing well. They're wider. They're to the side of the red line. So when I look at this, it tells me that I need to increase the number of clusters, right? I want to try to get those 2 diffuse clusters to be more focused. And so you can actually do that in an automated fashion using elbow plots. And so what we're looking at here at this top elbow plot is we're trying every number of clusters between 4 and 11 and refitting the model with that new number of clusters and looking for the point where our average silhouette score reaches its elbow, right? Its peak. And so here, this tells us that the optimal number of clusters is 8. You might also see something like this bottom plot, which tells you that centroidal clustering is not working. And so if you see something like this where the elbows are all akimbo, it tells you that maybe you should try a different clustering methodology. I'd look at this and maybe my next try would be something like agglomerative clustering, something that's more hierarchical and not trying to fit everything into spheres. So we talked a little bit about trying to get to that middle regressor, the one that had kind of a smooth curve without going through all of the points. The way that we do that is with regularization. And the rule of thumb for regularization is to use lasso, elastic net, or ridge. But you still have to decide, you have to pick a hyperparameter for the alpha value. And that tells you how much to smooth out the curve. So how much to squish all of the aggressive wiggles that your data wants to tell the model to do. And so as we add more alpha, we have less complexity. So alpha goes up, the wiggles go down. But we don't want the wiggles to go down too much because then the model isn't going to be predictive anymore. It's just going to be a straight line and not tell you very much. So alpha selection in Yellowbrick allows you to search between a range of alpha values and see the point where error goes down, but you don't increase your error, right? And so here we can kind of see that our optimal amount of alpha is around 4.25, let's say. Okay, so last couple of slides here. Using Yellowbrick, I think, is very easy if you already know scikit-learn. If you don't know scikit-learn, we have a really good intro guide in our documentation. You can quickly install Yellowbrick from the Python package indexer. If you're a Conda user, you can Conda install Yellowbrick. And then at the bottom, I've got a link to the documentation, which has lots of training materials and resources and examples and stuff for you to use. If you are interested in becoming an open source contributor, which I would encourage everybody to consider, a lot of times when you're getting started in data science, the wise advice that you get is build a bunch of projects in your GitHub repo that you can show off when you go interview for jobs. And that is good advice in the sense that it will tell people that you know how to do data science, but it's kind of hard to get started on doing a bunch of projects all by yourself when you're an intro level data scientist. One way to kind of get around that is by contributing to an existing open source project that does data science and machine learning, and Yellowbrick is a really good candidate. We are a very open and welcoming group of contributors. We have 70 contributors now. The package has been going for about 5 years, and we've accumulated one of the most diverse groups of contributors in the Python community. And we really are welcoming of any contribution, however big or small. And we kind of have this goal internally of being kind of the best first place to contribute. And I might have stolen that from another company, but I think that idea of being the best first place to contribute to open source is really what we're going for. And so in closing, my final slide, I will ask you all please to visit the Yellowbrick page on GitHub and give us a star. You can do that in the upper right-hand corner. And if you do have questions, if you want to talk more about hyperparameter tuning or heteroscedasticity or whatever, feel free to reach out to me on social. And I'm not sure if there is time for questions. Is there anybody here who's in charge of the conference? No, so we get to decide. So I'll take a few questions if you'd like, and then probably you'll want to get going to the next discussion. But thanks very much for your attention.